Hello, welcome back to COG 266, Brains, Minds, and Consciousness. So, today we're going to carry on in our journey towards understanding how brains do what they do, if not why and what for and what capabilities they have, at least just how the mechanisms function. So, today we're going to talk about brain signaling. This is the idea that, somehow information is moving around between your neurons. Now, we've touched on this several times. We've talked a little bit about, neurons are able to fire and they're able to affect other neurons, and they are extended out so they can touch things far away and things nearby. And I think we basically understand that neurons are the wires in the brain. But now we're going to get into the nitty-gritty of how they actually achieve transmitting information when they are biological cells. They don't have brains and eyes. They can't read text and say, hey, look, Dave, here's what this text said to me, right? They have to do something chemical. They are cells, so they have to do something at a lower level. Let's talk about that. So, quick reminder of where we've been. So brain is the bulk of what we'll talk about. We've started out with why should we care about the brain, and I think we all had an intuition on, it's super important, but we kind of walked through the history of why people began to care about the brain. We've also talked about how to measure the brain, what's some of the basic organization of the brain. Now we're going to talk about how do neurons even do the things that they do. So that's where we're at. So, let's talk physics. How do neurons produce the signals that they use to communicate with each other? And it all starts with physics. Physical properties of the atoms of a cell give rise to the ability to move electrons around. Now, electrons in the form of ions, technically, but the idea is that these are electrical changes, right? There is a change in the electrical patterns, and that's why we're able to detect certain things about how neurons are moving the information around, right? So let's again dig deep into physics. Physics. Matter is atoms. I think we all probably know this by now, right? Atoms are a super basic unit of structure in the universe. We know a little bit more now that there are things below the atom, but gets all wibbly down there. So we'll focus on the atom as our basic unit today. Atoms have neutrons, which are neutral, protons, which are positively charged, and electrons that are negatively charged. Right? So protons are positive, electrons are negative. Most atoms are balanced with the same number of each of these types of particles attached to the atom. Hydrogen, for example, is one proton, one electron. Helium, the next one over, the next least complex atom, has a little bit more going on. It's got a couple of each and a couple of neutrons, although some of them have wildly different amounts. These are basic. These are atoms at their simplest form, right? You look at the table, the periodic table of elements, the hydrogen and helium are right in the top row, right? They are the least complex atoms. More complex atoms have more interesting properties, and they have certain things about them that lend themselves to becoming charged in different ways. For example, potassium, our friend from bananas, right? It's more complex, but it still only has a single outer electron on all of its rings. Now, think back to a little bit of chemistry stuff. I can go back. Hang on. Each one of the periodic table is organized such that each row represents a number of electrons that fit into one orbital. So if we now look at this, potassium has 3 orbitals that are full of electrons. Go back again, I'll show you. Potassium is K, right? Down at the row 4, first column. That means that it's going to have 3 full orbitals, and then it's going to have 1 loose electron. Sorry, I'll stop jumping back and forth. That means that it's easy to add and subtract that electron. Now, I can't tell you exactly why potassium is the key thing here. It might just have to do with how tightly each orbital binds to the atom, something. I am not a physicist. But potassium creates this environment, this particle that can easily become a very stable positive ion, K+, right? So that means it's able to destabilize charges elsewhere. It's able to interact, right? When most particles, most atoms are quite stable, if they are stable, it makes it so that they don't care, right? They don't need to interact with other things. All the noble gases on the very right-hand column of the periodic table, they don't need to do much, right? They don't interact with most other particles. However, potassium is a strong interactor. Now, there are others like this. So there are lots of ions that are doing stuff in the brain. Potassium is positive, sodium is positive, Na+, chloride is negative. Now, you might recognize that as sodium chloride or table salt. Yes, we are salty creatures. Calcium, very big in our bodies and in our brain. Double positive there. So what's happening is when the ions move around, they are creating electrical current. And that's sort of the primary way, at least that we measure what's going on in the brain, the signaling in the brain. And it's also just, it's all the mechanisms are all tied together like that. So these ions are a fundamental part of how neurons get their work done to send information around. So the way that works in a broad sense is it's the concentration of ions in the cell that will determine its current charge, its current state, right? If there's a lot of negative ions inside the cell, that's a very different world than if there are a lot of positive ions inside the cell. And the way the cell regulates this is that there are these pumps, protein channels, on the surface of the cell, on the cell membrane, that are able to move ions in and out, depending on what needs to happen, right? Now, that's often feels like, oh, I'm giving the cell some kind of agency. We'll talk about how these different changes are triggered, but the idea is that these pumps are one of the fundamental movements in the cell. So one of the ways that it says, hey, something's happening inside me. I need to eject some negative ions out into the world or whatever. I need to change my current charge inside my cell. Here's a diagram of this. Here's the cell membrane. And here in the middle of it is a pump, one of the protein channels. Cell membrane. On the outside of the cell are some particles, some atoms floating around, some ions. Outside the cell, in this particular case, are a lot of sodium atoms and ions, and chloride ions. A lot of, again, salty. This means also unless you're fluent in chemistry, you don't need to worry too much about the positive and negative charges here. The key is that outside, this combination of ions creates a positively charged environment. These particles they want to give away an electron. Whereas on the inside of the cell, in this case, we've got a lot more K+ ions. They are negatively charged. They want to receive an electron. So what this means is that there's a difference. There's a differential between the inside and the outside of the cell membrane. This cell has a certain amount of potential to act, for something to change. So the membrane potential ends up being the difference in the electric charge across the cell membrane, so from the inside to the outside. If they were equal, the cell would be kind of inert. In this case, the cell is kind of primed for something to happen. What? Well, we will continue. So, at rest, neurons are a little bit negative, just by their nature. And so it's easy for ions to cross the membrane, especially these positively charged K particles, these potassium particles. So, in general, particles will move in and out of the cell pretty regularly, and across these different ion channels. So under normal circumstances, when a cell is just like hanging out, relaxed, it's a little bit negative. It's a big mood. So how do these ions become signals? I hope we're getting a working understanding that like the cell can move them in and out, and that changes the relative charges and something. Okay, what do we do with that information? So there are three kinds of signals that result from ions crossing the membrane of the cell. There's receptor potentials, so those are the ones that interact with the actual outside world, responding to things like pressure and light and chemicals. We'll talk a little less about those today and more when we get to like specific senses, discussions of senses. So that's the receptor potentials. But there's also synaptic potentials. So the ones that connect axons and dendrites, right? So the ends of one neuron with the beginnings of the next one. So neuron to neuron. And there's two kinds there. There's excitatory, which makes the membrane more responsive. So, hey, this cell should probably wake up and do something, says the excitatory communication. And then there's inhibitory, which says, hey, this cell doesn't need to react to the things that are happening around it. And again, there are ways that we can describe how that happens. But first, let's look at some of the way these things sort of make sense in terms of, hey, we're trying to send signals, right? So here's two neurons. One of them is a receptor neuron that's having some kind of action on its far end. I'm pressing on it, right? Some kind of stimulus from the outside world, right? So this neuron, its receptor areas will take some kind of amount of activity from the stimulus itself and convert that into a strong or weak sort of charge inside of itself. When that charge is stronger, it will cause the axon to fire several times, fire over and over. And again, we'll discuss how that kind of cascading happens. Stronger inputs will make it fire faster, right? Then, in a similar fashion, although in a way that's completely unrelated to the original stimulus, it is now fully in neuron communication mode, the next neuron will actually capture something like that same strength of stimulus from the previous neuron. It will convert in the dendrites, they'll capture, signals coming in at a certain rate, something in me will change only so much given that rate, and it will cause me to replicate that signal and pass it forward. You see how the spikes in each axon on the two different kinds of neurons here are doing roughly the same thing. The message is getting through. And compared to the strong stimulus, again, double the number, maybe 7 spikes there, from a stronger stimulus, brighter light or a harder pinch or whatever, the message is carried through as well by the dendrites catching these different. So the ends of the one neuron are producing some kind of potential that the next neuron catches. Okay, so let's talk about why that's possible. Ions are getting converted to signals. So in an excitatory potential, neurotransmitters that come out of the end of one neuron, and we'll get back to them, but we got to start somewhere. So the neurotransmitters will come in and they'll say, hey, protein channels on the next cell. you got to open up, and you got to let more potassium ions move across the membrane, creating a stronger negative electrical impulse inside your cell body. Now, that will, the more that happens, right? So the more these neurotransmitters come to the surface of the next cell, and they say, "Hey, you got to open up. You got to let some of these negative charges in." The more that happens, the more likely the cell is to now start its own firing process. Whereas an inhibitory control will do the opposite, causing less activity. It'll say, don't worry about those channels, don't open up, you don't need to do anything. This has to do with how exactly those will stimulate and inhibit each other. But in both of these cases, the reactions are proportional to the size and strength of how much each synapse is connected to each other, right? So in this previous example, we see that there's three. All of the nodes are connected from one to the other here, so there should be very little loss of signal. In other cases, maybe lots of different neurons are connected to each other, right? It's not just a one-to-one scenario like we're seeing here. So that has to do with the weight, so how much one neuron is connected to another one nearby. Okay, so this is how I hope we're starting to see how the cells will get stimulated. Something will come in and say, "Hey, open up the gates or close the gates down," right? You should be more active or you should be less active. What does active mean? So, action potentials, this is the most common thing you'll hear about in neurons. They start as the result of lots of synaptic potentials coming in, right? So as we saw, a bunch of spikes had to happen in the example. Keep running back to it. Lots of spikes have to happen here, right? For the next neuron to pass the same number of spikes along. So they start by the dendrites will gather these, they will be told, hey, let more negative charge into the cell, right? That will gather in the cell body, will become more and more negative until when it fires, it travels down the axon all the way to the terminals. It creates this sort of cascade that says, oh man, my cell body is so negative right now, there's going to be a switch that happens that makes this thing fire. So as the synaptic potential continues to increase along the membrane, there's a feedback loop that occurs. So the membrane gets depolarized and it says, oops, I'm going to open my channels rather. More negative stuff is going to flow in and they're going to repeat. We're going to pass it down. Keep going. Keep sending this. So what happens is a spike will occur. And there's a lot of spikes can happen in a row, but the idea is down the whole length of the axon, the change of the negativity inside the cell will actually trigger the channels that let ions in and out, trigger them to open. So it will send proximally down the length of the cell. The sort of message will move, right? Hey, but my cell body has gotten very negative. I've been told by many, many sources that I should act. So the way it acts is that negativity will trigger down the axon the movement of the signal. It's hard to visualize. We're going to keep going here. We're going to keep getting at it. So the spikes that happen, they're rapid increase in the membrane potential, right? A lot of sodium will flow in, and then potassium will flow out, followed by a rapid decrease back below some threshold at which the thing will start doing it again, right? So, okay, an action potential is a single firing of the neuron. It's going to do it a lot. It needs a little bit of time to recharge, but there's something called the refractory period we can talk about. But in general, action potentials are this sort of, there's no going back, right? It's all or nothing. The properties of the cell means that They're going to be kind of the same every time because the cell is going to be triggered the same way every time, right? So it doesn't really matter how strong it is because all that matters, is whether or not this thing is happening or not. So that's notable. It doesn't matter how strong one neuron's action potential is in terms of its amplitude, how negative it becomes, how charged it becomes. What matters is the frequency, how often it fires. If it's really stimulated, it's really excited because of the excitatory connections coming in, it's going to just keep firing rapidly over and over because it's got a lot of signals saying, hey, open the gates, open the gates, open the gates, right? It doesn't matter how negative it actually gets. It only matters that it keeps crossing this threshold, fires, moves back down, crosses the threshold, fires, moves back down. Okay, so frequency is key. And it basically has to do with the relative rate of the synaptic potentials coming in, right? So the more excitatory synaptic potentials you get, increases the frequency of the firing of your cell, and the more inhibitory signals you get, the lower the frequency. Once again, kind of taking it down again, thinking about the way information comes in, right? A previous cell, maybe from a sensor, or maybe from a different a different neuron coming from somewhere else in the brain, it's sending out from its axons little neurotransmitters that say, hey, next cell, open the gate, right? And it will, the dendrites start to do that. They will open their gates and let more charge into the cell. The inhibitory synapses, though, come into the cell body typically, and they say, hey, don't worry about what the dendrites are doing. Close down a little bit. Don't necessarily react too quickly, right? So those combinations, the combination of those two different messages to the surface of this current neuron combine, and you get sort of a situation where eventually, if the neuron accumulates enough excitatory potential, enough negative charge inside the cell, it will fire. And it will fire, again, by the message will travel down the axon and say, hey, let in the negativity, and then your neighbor will do the same, until we get all the way to the end and we communicate to a new cell. So, let's look at the combination of these two things. So, the excitatory and inhibitory situations, right? We have lots of excitatory potentials coming in so follow left to right, right? Excitatory potentials come in, and the cell body grows and grows and grows. Its charge continues and continues. Also, don't worry about the axis and the positive and negative stuff. Electrons are weird, right? I may have misspoken here and there. I apologize for that. The key question is the charge inside, so the amount of potential going on inside. Whether that's negative or positive, that matters, of course, in the chemical sense and the physical sense, but I'm just saying, if that starts to trip you up, focus less on that and more on the idea that some kind of charge is happening inside the cell. It's accumulating, and it rises, and it rises, and it rises until it gets to a point where it shoots up, and then it sends the information on, and then it falls back to Earth, right? So that's that first hump right there we're seeing. It does it again and again, right? This is the spiking that we're getting. So these excitatory signals are coming in, and they build up inside the cell until it spikes and fires, and then it falls back down to where it started. Spikes and fires, falls back down, spikes and fires, falls back down. Then on the fourth run, we start to get an inhibitory signal, which prevents, so even as it rises, as the activation rises, as the charge inside rises, accumulates, now a new signal comes in and says, yo, stop, don't worry about that. And it does. It shuts down the opening of the channels, and we never reach that threshold where the cell is going to send the signal. So an inhibitory impulse will stop the firing, whereas the excitatory ones will cause the continuous firing. So, a neuron's output is going to be the sort of the sum of its excitatory and inhibitory inputs, right? In that last slide, boop, for a long time, the sum of the inputs were all positive. So the inputs are coming in, doot, 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 those little tick marks there. And that means that the activity in the cell, the firing rate, is going to be a constant, hey, here comes the signal. And then eventually, though, we start adding this inhibitory thing that kind of zeroes it out. That is the sum of the excitatory and inhibitory signals is now 0 or less. So now nothing changes. So, if you've seen neural networks, this is the same idea of weights and how you combine inputs from various nodes mathematically, but it's doing it in biology, which is very cool. So, okay, that's the idea. I hope you're now understanding more about what the sort of how we count action in a cell, right? And I've given you a gloss over of how this information actually moves down the cell. So let's try to focus in on that a little more. So when that action potential occurs, what it's going to do is propagate down the length of the axon, right? The potential, again, it doesn't matter so much. The size, right? The charge, the amount of charge doesn't matter so much as it moves down the length. And you might ask, why is that the case? Well, remember, the axon is skinny, right? It's the thin part that protrudes and moves down, and it's always kind of the same, diameter, more or less, if we're measuring it by volume, right? So the size of the signal doesn't matter. It's the fact that it is firing that matters. So let's have a look. Okay, so this image is showing some membranes, right? The membranes of the axon, and it's showing sort of a scenario of there's negative charges inside and positive charges outside, or negative ions inside, positive ions outside. Okay, right. So what's happening is as one little region inside the cell, starting with the cell body, right, it has accumulated a certain amount of action potential, right? It gets to a certain point. And what that will do is trigger the pumps on the cell membrane to exchange their ions, right? Now, this happens one segment at a time. The only reason it moves only one direction is that the idea is that it will spread, right? So each little region that is currently hyperactive will now pull in lots of positive particles, and that will destabilize the next area. The only reason it only moves one direction is that the channels behind it, they're kind of shut off. They've already done their work for a moment. They can't work again yet. So what that comes down to is it's sort of a rolling downhill, right? You have a lot of action potential starting in the cell body, and then that will activate the axon closest to the cell body, the little segment of axon close there, which will destabilize itself and cause the next segment of axon to become destabilize the next one over and over and over and over and over until you get down to the end of the cell. I hope that tracks. I hope that's making sense. So the action potential itself it's not a real, it's not a thing. It's a pattern of ion activity that is moving, in a sense, across the cell, even though none of the parts of the cell are actually moving. It's just a local field of charge that is moving, and it's doing so by pulling ions in and out of the cell. Okay, I hope this makes sense so far. That the charge comes in, it makes it want to charge the next part of the cell, which will charge the next part, all the way down the line until we get to the axon's end, the terminals. Okay, some features of this phenomenon, right? So this is the fundamental piece of how the information will move forward through one of the cells, right? So one question you might have right off the bat is, how fast does this actually move? In vertebrates, it's about 100 to 200 miles per hour. I mean, I know it's not traveling very far, but this is roughly the speed at which a neuron can shoot its signal across itself, right? And it's facilitated by a glial structure called the myelin sheath, which I've brought up before. Sheaths are a certain length that, if you think about this process, if you have to wait for each set of channels to destabilize and then do their ion swapping trick to cascade down to the next one, if you have to wait for each one, it's a little bit slower, right? You are waiting on each individual notch of the neuron to do its work. So to speed this up, animals with this kind of trick up their sleeve are able to, they have these myelin sheaths that say, nothing's going to happen in this section. Destabilize a little more in your section, and that destabilization will pass faster to the next site. So looking at this, you can see, first of all, how a myelin sheath comes to be around. This is sort of a cross section, right? You can see a little bit in the thick part of the myelin sheath where the axon of the neuron is wrapped up in this kind of fatty tissue. What that does is, again, it makes it so that the distance between each destabilization kind of moment in time is further. So you can go a little faster. And you don't risk, interacting with too much with things around you. So you are insulated. It's a bit of a highway situation. So that's how we got so smart, is these myelin sheaths are very useful for speeding up interaction and also helping to make neurons able to kind of send over longer distances within the brain and in the other nerves, other parts of your body. So this, I hope, is helping to make sense of what the action potential is and what it does. We should talk about after the action potential. The cell membrane is going to fall back below resting potential, and the ions are going to kind of flow back to equilibrium. The refractory period in a cell is a time of limited activation. So it's harder to fire a cell that is in its refractory period. It's not impossible, but it's harder because the channels are tired, right? The membrane is like, leave me alone for a second. Now, if you think about this, why might that be something useful for us to have evolved? Well, if you think about that basic image, what might be the problem if there was no such thing as a refractory period, at least on the surface of the membrane? Well, there would be no directionality here. Every destabilized area in the neuron would then just trigger the things nearby it. So it wouldn't have a direction. It would still reach the end of the cell, but the whole rest of the cell would still be destabilized. It wouldn't possibly work. It would just continuously fire forever. And that's not a great way to be as a cell that's trying to do a particular job, continuously firing. So that's why this refractory period, it makes sense in a general sense. It's not, the magic wasn't guided towards this or anything, but that is how this is so important to the function of the cells. So again, refractory periods have this time of after a spike happens, you gotta wait a sec. Not a second, that's way too long, but you gotta wait, a beat, a neural beat. So the overall flow is upstream neurons somewhere, something else, some other neuron from some other place. We'll talk about how signals get into neurons in the first place eventually, but for now, just think about this as upstream neurons. They're connected by a synapse, and they cause some kind of variation in the membrane of the current neuron, right? The one that we are currently talking about. They might excite or inhibit that neuron's membrane by sending neurotransmitters to say, hey, do things, wake up, or hey, shut up, don't do things, right? all about the pumps, right? So what that does is it varies the potential somewhere between the resting potential and the threshold for the cascade we've talked about to happen, the activation. So when that threshold is crossed, when enough charge, enough action potential is built up inside of the cell, then this cascade of propagation happens where the membranes, each in turn next to each other, say, oh shoot, I'm going to charge. Oh shoot, I'm going to charge, right? And they carry it all the way down the end of the cell to the axon to send off to somebody else next time. So now that's how we have got that. I hope this sort of illuminates how one single cell is able to take input, wait until it's necessary to fire, and then send the information on. And then again, there's this brief refractory period where the thing can't fire again, because that's sort of important to the mechanism. Okay, that's what I'm going to call it today. I'm trying to make these lectures a little bit shorter than the full 55-ish minutes we've been hitting. So saving some for next time. We can recap some of this next time as well if it's not all landing perfectly. It's a complex phenomenon, and it's tricky to describe it in a way that can hook into you. So next time we're going to talk more about this same kind of idea, but more on the output end, right? So messaging forward. How do neurotransmitters that are released by one neural cell impact how the next cell functions? Why is it possible for that to happen, right? And we're also going to have a fun, scary-ish but fun romp into toxins of all kinds. So how jerks like scorpions can screw with your neurotransmitters to cause you grief. Okay, so look forward to that. All right, so final thought, as always. At the scale of a single neuron, the ionic charge inside of the cell builds up until it triggers an irreversible cascade, sending the signal on to the next cell. Think of a phenomenon at a larger scale that has a similar point of no return. In your body? In physics, maybe? Social dynamics? Astronomy? How are they similar to the neural cascade? How do they differ? All right, that's it. Thanks. Take care.